Welcome back. So we've been studying thermomechanics, and we've studied various aspects of it. We've looked at the first and second laws of thermodynamics. We used the Legendre transformation to introduce this Helmholtz potential, and then we did further things with it. Right? We looked at how it helps us reduce the balance of energy down to an equation for heat transport. And then we also looked at the effect of thermoelasticity, right? At how the coupling between heat conduction and nonlinear elasticity works out into the heat transport equation. There's one little detail I want to add to our treatment of thermomechanics, and that is the question of the heat flux in the current versus the reference configuration. All right? So that's where we're going to start our study today. And I'll title this segment the heat flux vector in the current and reference configurations. All right. So the setting for our treatment is the balance of energy, the first law, in the following form. Okay, so let's recall the first law in the following form. We wrote it as rho 0, material time derivative of E bar with respect to T equals rho 0 times R bar, where R bar, if you recall, is the local heating, minus divergence of the heat flux vector, and I believe there is a J here, right? Okay, and this plus J times Cauchy stress contracted with the rate of deformation tensor. All right? Now I won't rewrite what everything here is except for what the heat flux is, because that is the object we want to talk about a little more right now. Okay, so Q is the heat flux vector defined in omega t. Okay, and it is defined in omega t because of the way we first obtained our first law of thermodynamics. If you go back a few segments, you will recall that our treatment involved looking at a body not in the reference configuration but in the current configuration. And then in that setting, we said that, okay, on a surface, we may be providing we may be controlling the amount of heat influx into the body, right? And I'm sure I said it back then as by saying that, well, we can consider that either the orange part or the blue part of the surface of this ellipsoid is the part of the boundary where we are controlling the heat flux. And then from there, and this was all set up in the current configuration, right? So in the current configuration, we said, okay, this may be a unit normal, and then we can talk about how the heat flux is being controlled, the heat influx is being controlled over the current configuration. Okay? So it was in that setting that we talked about the heat flux vector, right? So it was properly the heat flux vector in omega sub t. So it is defined as the quantity of heat crossing a unit area, okay, where that unit area is in the current configuration. Okay, so it's quantity of heat crossing a unit area in omega t, and it's crossing that unit area perpendicular to the unit area. Right? In order to speak of a unit area, we obviously need to have some surface, right? And so we're saying it's the heat flux, it's the amount of heat going perpendicular to that surface in omega t per unit time. So the picture is something like this. We have our basis, and that is omega sub t. Suppose that we have a surface, an internal surface, right, within the body, right? So I'll try to demonstrate that it is a surface by, I'll try to indicate that it's a surface by drawing these, right, things that make it look like a surface. Okay. And what we're saying now is that the heat flux vector is that. Right? We tend to think of it as the amount of heat coming out perpendicular to that surface per unit time. Okay? What we want to do now is understand how to rewrite an equivalent heat flux vector in the reference configuration. Okay? So how is Q related to heat flux in omega sub 0? Okay? This is the question we're attempting to answer. This is the question we're asking. The way we approach it is in a manner that is very similar to the way we approached the equivalence of different stress tensors, right? The way we introduced different stress tensors, starting first with the Cauchy stress. Okay? So the approach is the following. Okay, now since we want to talk about the current and reference configurations, let's start by putting them both down here. Okay, this is omega sub naught, omega sub 0, and let us suppose that this is this subset of the boundary is the heat flux boundary, right? So here I will call it partial of omega naught capital Q, all right? And in the current configuration, I will call it partial of omega naught sub t, also capital Q. All right? Fine. So what we want to say is the following. Supposing this is the normal, right? Or suppose that is our area vector here. Capital N dA, and that vector gets transformed into little n dA, okay, area vectors. What we want to say is that we are controlling the total amount of heat influx here, and let me denote that by just writing the letter Q naught here, okay? So that is the total amount of heat that we are putting in to the body over that area vector capital N dA in the reference configuration. Okay. Now, just as we did in the setting of stress tensors, we note that the only way to talk about equivalence of heat flux vectors between these two configurations is if we say that something is the same between these two configurations. We're talking of heat here, so what we are saying is that the heat flux, that the heat influx to the body is the same in both configurations, right? And that is perpendicular, right? That area vector is perpendicular to the current configuration. Capital NdA is the area vector perpendicular to the surface in the reference configuration. What we are saying is that between these two configurations, the amount of heat we are sending in through that surface, and this is what we're controlling, that is the same. Okay? So, the picture here is this. Reference configuration, current configuration. The physical equivalence here that we are making in the context of heat is that if this is the heat influx boundary, we're saying that the amount of heat we're providing here, over this area per unit time is the same as we're doing back here, okay, in the current configuration. Okay? All right? So, what we're saying is that the heat flowing in per unit, sorry, this is not per unit area. The heat flowing in over NdA, that's the area vector in the current configuration, is the same as over capital N dA. Okay? What this means is that we have Q naught equals minus Q dot N d little a, and we have the minus sign because NdA is the unit, NdA is an area vector, but that's directed outward. Okay? All right? So we have a minus sign here because we want to talk about the heat flowing into the body. All right? So that explains the minus sign here. Okay? So that is in the current configuration. In the reference configuration, we want to say that this is equal to minus a heat flux vector in the reference configuration, which I'm going to call Q, okay, at the small risk that this may be confused with our standard rotation tensor. Okay, so let's remember that they're different here. Okay, just by context. Okay, so it's minus Q capital N dA. Okay, where the idea is that this quantity is the heat flux vector in omega naught. Okay, note that this is not a rotation tensor in this context. Okay? All right, so this is the setting. And if you compare this with the way we treated the problem for equivalence of stress tensors, we said a similar sort of thing, except that back there we said that the total force that is being applied over each of these area vectors in the reference and current configurations is the same. Okay, and then it was on that basis that we defined the different stress tensors. Okay? So, essentially the same sort of argument, the same sort of physical and mathematical idea here. Okay, how do we proceed? Okay, we'll go to the next slide. To proceed, we recall Nansen's formula. Okay, and Nansen's formula is little n dA equals J, the determinant of the deformation gradient, F inverse transpose capital N dA. All right. Okay. When we have this, now we can go back, and it's just a single step that we need to complete. Okay. So we apply this to the statement we had in the previous slide, which is that minus Q dot N dA equals minus Q, capital Q, dotted with N dA. Okay? All right? Remember that both of these things give us heat flowing into the body per unit time. Okay? So we get minus Q dotted with J F inverse transpose N dA equals minus Q, capital Q, dot N dA. And then by observation, we note that we must have, well, okay, let me do just a little more work on this. I'm going to write this as minus J Q dotted with F inverse transpose N dA equals minus Q dot N dA. Okay? And now from our study of how transposes of tensors work across dot products, what we know is that minus F inverse, sorry, I need to have a J there. Minus J F inverse Q equals minus Q. Okay, by observation, and we can look at it in indicial notation and also make sure that things work out correctly, and we'll do that. Okay, which then of course this means that the relation between the heat flux vectors in the two configurations is J F inverse Q equals Q, capital Q. Okay, where little q's in the current configuration, capital Q's in the reference configuration. Right? Just to be sure about how this works out, let's look at coordinate notation. Okay, coordinate notation applied back to that line. Okay, so we have minus J, J being a scalar. Okay, Q, now Q lives in the current configuration, so let's give it index lowercase I. All right, now this is acting on F inverse transpose. Okay, now F inverse transpose has indices little I, capital I. Okay, and N has index capital I, and then we have dA. Okay, now on the right hand side, okay, by comparison, we must have Q, capital I, sorry, minus Q, capital I, N, capital I, dA. Okay? And you remember how the transpose works, right? So what this tells us is Qi F inverse capital I little I n capital I equals Q I n I. Okay, and I note now that I am missing a J on the left hand side here. Okay? Now we take this all over to we'll go over to the next slide here and observe that what we have is, just rewrite what we wrote there. We had J, we had F inverse, okay, and using the fact that these are just multiplications and multiplication is commutative, we have F inverse I little I Qi acting on Ni equals capital Q I Ni. Okay? And clearly now, by observation, we see that this does indeed satisfy the condition that the relation we wrote out previously, which is that J F inverse little q equals capital Q. Okay? So this is the relation between the heat flux vector in the current configuration. This is in omega sub t, and this is in omega naught. Okay? All right. Now another exercise that you may want to try out is to look at the balance of energy, the first law of thermodynamics, which is written in the current configuration, and use this little calculation we did to write that first law entirely in the reference configuration. Okay, we've gathered quite a bit of expertise in doing that. It should not be that difficult of an exercise, and it's worth trying on your own. All right, we'll stop here now.